Hi, that we continue the Poisson regression. So we now define what the Poisson regression is. So suppose that the yi is the count random variable and xi are predictor vector. Xi is a predictor vector. Then Poisson regression that assume that the y basically follows Poisson random variable with parameter mu I. So the data point have different predictors. So mu I is different depending on I. And here, the log of mu I is equal to the xi transpose beta. We also name this as eta I. So in the same way as logistic regression. And here, as we mentioned in the previous video, the expectation of y is mu and variance of y is mu. So mu is controlled by this x, and we have parameter beta. So our objective is to estimate beta. Then we can estimate probability of yi is equal to y. And estimation is done by likelihood method, so maximum likelihood. So if we just write down the likelihood function, the log of likelihood function of this Poisson random variables, then we can get the likelihood function. So this is just the straightforward conclusion of the likelihood function. So just the original variable that we take logarithm and the plug in the log of mu is equal to xi transposed beta, or mu I is equal to exponential of xi transposed beta. So this is mu I. And this is the log of mu I. Then you can see why this is the log likelihood function. And to get the estimate for beta, that we have to maximize this function. So we differentiate this with respect to each beta j. So beta is a parameter vector. So for each parameter vector, the element of the parameter vector, that we differentiate the L beta by that parameter. Then we get this formula. So this is highly nonlinear equation because we have exponential of xi transpose times beta hat. So it's not as easy. So beta hat, to get beta hat is not as easy as linear model, but at least the model, the formula looks similar to linear regression model. And if we denote this as mu hat, you can write this as x transpose y is equal to x transpose mu t. So here the t was the typo, so this is transpose. And here, so this equation holds for each j, and this is matrix form. So just we summarize in just one equation. So this maximum likelihood method can estimate the beta. So next one is testing. So whether or not our model is appropriate. So that is one test. And the other test is to compare the two nested model. Larger model is significantly better than the smaller model. So we would like to answer that question by testing. So for testing, we define deviance. So it's similar to logistic regression. So suppose that the proposed model M have likelihood function L sub M, and another model, which is perfect model with n parameters. We have n observations, so the perfect model has n parameters. If we have n parameters, we can explain everything. So that is the L infinity. And the deviance is defined by -2 times the difference between log likelihood. So log likelihood Lm, so this is smaller model and this is the largest model. So this is large value and this has small value. So small minus large, so that is negative. Then we multiply by -2. So this is positive. So this is always positive. And to be exact, this is calculated by this, because basically the L infinity. So for this one, that we replace the mu I hat by yi, because this is perfect model. So mu I hat is the estimate for yi, because expectation of the y is equal to mu. So that makes this quantity is equal to this. Then we can use the chi-square test. So reject the null hypothesis that our model M is true if this is larger than the upper quantile of the chi-square distribution. So this is chi-square test. So we have the chi-square value here, and so this is the density. And we have chi-square distribution. So if we take the area of alpha here, then so this point is the upper quant point over here. So if test statistic is larger than this threshold, then we reject null hypothesis. So we reject. So that means that our model is not sufficient to explain the situation. And also the two nested model case. So if we have the model S and the model M, and the S is nested in M, suppose that LS is the likelihood for S and LM is the likelihood for M, then calculate the log of LS minus log of LM and multiply by -2, then this follows chi-square distribution with degrees of freedom D. And here D is the difference in the number of parameters for S and M. So if S have 2 parameters, M have 5 parameters, then difference is 3. So D is equal to 3. So this is how to estimate and parameters and the testing on count regression, the Poisson regression. Okay, so and another test it can be done. So in the previous page that we used the deviance, so that is basically the likelihood. But also that we can do this approximation. So this is so-called usual the chi-square test for goodness of fit. Probably you have studied this in more introductory statistics course, such as 20-10 or 50-30. And this is again the chi-square distributed, and the quantity is here. So this is the observed value minus expected value square over expected value. But now that you can see that this is a kind of natural shape. So mu I hat. So mu is basically the expectation of y. So estimated, so it's slightly different, but this is expected y. And this is expected I, but actually the variance is also this. So that you can see this is variance. So, and the numerator is square. So you can see that the yi minus mu I hat divided by square root of mu I hat. So this is actually the y minus expectation of y divided by standard error of y. So this is standardized. This is standardized. And the yi, so yi is count, but the count with the large possible so-called denominator is approximately normal. So it's similar to the count, the binomial data. So if we have the sample proportion with large n, then the sample proportion is almost normal. So here that we have the same thing. So yi is count. If count is large enough, then okay, so this is approximately normal 0, 1. So this is just approximation, but if we use this approximation, basically the normal square is chi-squared. So this summation of this follows chi-squared distribution. And here degrees of freedom is n minus p, and p is the number of parameters in the model. So we have the sum of the n terms, but the degrees of freedom is n minus p. So that is because the mu hat, to estimate mu hat, that we used the p parameters. So we lose the p degrees of freedom. And to be exact, we have to do some linear transformation to show that this is chi-square n minus p. But anyway, so this is the same as usual, the chi-square test for goodness of fit.